This conference will now be recorded.
So very good evening. We had been discussing the chapter. Yeah, good evening. Deepa, we had already completed this chapter nuclei. So today what I'll do, I have collected few numerical problems. These are all from old NEET paper. So those questions we will discuss today, so that you can also get some glimpse that how questions are being asked from this chapter in various competitive exam, especially NEET exam. So the first question, if you read, the binding energy per nucleon of lithium and helium are respectively given as 5.6 mega electron volt and 7.06 mega electron volt respectively. What is the Q value in the following nuclear reaction? So you look the nuclear reaction over here. So lithium and proton, they combine. That means you just bombard the lithium with proton, then the lithium actually produces two helium nucleus. Okay, two helium nucleus. Now you have to calculate what is the Q value. So binding energy of lithium is given, helium is given per nucleon. Okay, so how to solve this problem? You know, Q value is calculated as delta M into C square, because in this kind of reactions, what happens in the product, okay, reaction product has lesser mass than the reactants, okay, or sometimes these are called parent nucleus. This is lithium is parent nuclear, so that parent nuclear along with this proton, they have in total greater mass than the mass of these two helium. I am talking about atomic nuclear mass, okay. So since there is a mass defect or mass difference, that amount of, like, corresponding amount of that mass defect gets converted into binding energy, okay. This is according to Einstein's mass energy equivalence. So here already you can see the binding energy per nucleon. What is binding energy per nucleon? This is binding energy. Suppose this is binding energy, and binding energy per nucleon means it is divided by, actually this is given as Q value. This is not binding energy, this is Q value. Binding energy actually, binding energy per nucleon means binding energy, total binding energy divided by the mass number. So you look here, binding energy per nucleon is given for lithium and helium. So you have been asked to calculate what is the Q value. Q value means you have to take the difference in binding energy of the parent nucleus, binding energy, total binding energy of the parent nucleus, minus of binding energy. It is total binding energy of the daughter nucleus, okay. Then you get the energy Q value, whatever it is. This is Q value you will get Q value. Okay, so I hope you have understood this. As you do the calculation, then you understand. See, for the parent, how many nucleons? Excuse me. So there are 7 nucleons. So 7 into lithium has got 5.60 mega electron volt. I'll multiply with 7 because this is per nucleon, but I need to find out the total. So 5.6 into 7. Okay. Now you have been given the product over here. This is actually the binding energy of, see, helium is given. So binding energy of helium, and there are 2 helium. So 2 into 4. Okay. Into 7.06 MeV. So this is what you have to multiply. Then you have to find out. So if we do the simplification, then this turns out to be this. This is obviously the whole thing is MeV in MeV, and here this is 56.48 MeV. If you take the difference, so what you get? So it is actually okay. So here, since there is this binding energy is more, what you have to do? We have to actually subtract from the daughter to the parent. Okay. Yeah, obviously binding energy is more in the daughter. This is conceptually conceptually this is correct, that binding energy of daughter is always greater than binding energy of parent, and this is why actually this is actually one of the nuclear fission reaction. Okay. So we have to actually subtract from here daughter to parent. Binding energy daughter, binding energy parent. So if you take the difference over here, let me give minus sign over here, positive. So this will be positive, this will be negative. So you will look, you will get 17.28 MeV. Okay, which is nearly equal to 17.3 MeV. Okay. So this is the Q value for this reaction. Actually, this nuclear reaction, for this nuclear reaction, this is the Q value. So you need to understand that in the beginning we had done a small mistake, because conceptually this is correct. Binding energy of the daughter will be always greater than binding energy. Mass of the parent will be, or the reactant will be, always greater than the product, but binding energy will be always greater than the parent, greater for the parent, sorry, daughter nucleus. Okay, so this is the answer. Okay, so whether it is nuclear fission or fusion, always daughter nucleus will be having greater binding energy. We had already discussed that. So this is, I think this is a kind of, this is one of the fusion reaction where it is the proton cycle. So this is fusion reaction. Okay, all right, so we'll go to the next question. The next question says, suppose a radioactive element has half-life period of 800 years. That means what is given is T half, that is 800 years. How much fraction of the substance would remain after 6400 years? That means this time let us denote it by 6400 years as small t. So this is half-life of a radioactive element, and this is the time after which you need to find out the fraction of the substance or the nuclei, number of nuclei present in that substance. You know how substance like any radioactive nuclei decay. So decay equation, you know that, like after like as a radioactive nuclei is getting decayed at any time, how do you get the number of nuclei present? That is n is equal to n0 e to the power minus lambda into t. But if you know half-life, directly you can write this equation. The fraction means nt by n0. Okay, you can write this directly, half to the power t by t half. Okay, this is the, so this is the way you can do if the half-life is given, t by t half. Okay, so let us see what it is. So here in this case, the fraction substance, like fraction of the substance remaining after 6400 years will be half divided by 800. So this goes off, this is 8. So you get that fraction as half to the power 8. That means you get 1 over 256. So there is an option B, that is the answer in this case. So you have to understand, this is the equation for radioactive decay or law of radioactive decay. But when you have been given T half, okay, when you have been given T half, then you directly write this n by n0. This is the fraction of the substance remaining, of the substance remains after any time t. Okay, so this is the expression for that. Maybe I'll clean it, it is too much hazy. I'll write it once again, nt by n0. This is the fraction, this you have to write n0 half t by t half. Okay, that means in this case half to the power 6400. So this will give you 8, hence half to the power 8, which gives rise to 1 over 256. So this is the second question. So answer is this option B. So I hope you have understood this. We'll go to the next question.
Yes, sir.
Yeah. See, this question is also similar to the question. This is also from radioactivity. So we may use this law of radioactivity. N of T is equal to N0 e to the power minus lambda into T. This law of radioactivity, this will be used in this case also. Let us read the problem first. Suppose there are two radioactive elements A and B having decay constants. So there are two radioactive elements. There are two radioactive elements. Each of them has different decay constant or disintegration constant. So let us suppose lambda A is 5A, disintegration constant of the element A, and lambda B, disintegration constant of the element B, is given as lambda. And if at T is equal to 0, they have the same number of nuclei. So both of them are having same number of nuclei initially. That means Na is equal to Nb at T is equal to 0. If they have same nuclei, okay, the after what time interval the ratio of the nuclei present in the element A to that in the element B is this. That means you have to find out the time interval. After what time interval the ratio of Na to Nb, this is given as 1 by square. So this is the problem. You have to find out at what interval of time. Let me write. So these are the given things. I'll write this law of radioactivity only. Okay. Before that will be, let us assume that the time interval is delta t. So if I write the law of radioactivity for the element A, I'll be writing, let me write this as Na T over here. So initially it was Na e to the power minus lambda A into dt. So which I'll write as Na e to the power minus lambda A is 5 lambda, sorry, this is 5 lambda into here delta t. Okay, delta t. Similarly nb in bracket, actually it will be delta t only. So we'll write here delta t. After delta t time interval, so this is nb, I'll write directly minus lambda into delta t. Okay, so we have got this one and this one after delta t time interval. Now I'll be using this space. Let me write then Na delta t divided by, I'm just taking the ratio whatever I have got after delta t time interval. This is for A, so I'll write this is Na into e to the power minus 5 delta t into lambda. Okay, I'm just writing that. This is nothing new, whatever I have got I'm writing that only here, and divided by nb e to the power minus lambda, or let me write as delta t into lambda. So you look in the given condition at t is equal to 0. Initially, how much, like they had same number of nuclei. So that means this I can strike them out because we take this are equal. So what you get in the left hand side, they have been already given this ratio is already given. What is that given? The ratio is given as 1 by e square. And in the right hand side, if you solve, what you get, see, it will be positive, so it will be minus 4 delta t into lambda. So if I write this 1 over that, I'll write, since it is negative, I'll write this as 4 delta t into lambda. Okay, so I can just remove this part now. So this, look, this I have got 1 by e square is equal to 1 by e to the power 4 delta t into lambda. Now if you compare the power, okay, if you compare the power from here, I can write 4 delta t into lambda is equal to 2. Okay, that means delta t will be 2 by 4 lambda, which is 1 over 2 lambda. 1 over 2 lambda. Okay, so see here, the first option is 1 over 2 lambda. So delta t we have got. I hope you have understood this. If you have any doubt, you can ask me, Deepa. Do you understand this? Nothing. What I have done, I have just written the law of radioactivity after delta t time. In place of t, I have written delta t. In place of lambda, whatever lambda is given for the both element, I have written. Now this n0 is na and nb at t is equal to 0. So when I take the ratio that those things are equal, that's why I have strike them out. And in the given question, after delta t time interval, the ratio is 1 by e square. So that is the thing I have written in the left hand side. And right hand side, upon simplification, what I get is delta t is equal to 1 by 2 lambda. So this is how you have to solve this problem. Okay, so the option A will be the correct answer for this question. Now let us go to the fourth question. So this
Ram,
question,
no sound.
what about now, madam? I can hear you. I can hear you. What about now, madam? Are you able to hear me now?
Now I can hear you. Previously, what the low voice?
Oh, it was low voice.
Yes, yes.
So, like, how long it was low voice, madam? How long? For how many problems? For this only? No, I'm asking for how many, like how long? It is for 15 minutes or 2 minutes, 3 minutes? How long it was low voice? Okay,
Deepa
anyway,
heard.
now,
I cannot hear the sound, ma'am. Deepa also is facing the problem, it seems.
oh, is it?
Yes, yeah, now only she's sending the message. Only that 4 minutes or 5 minutes.
Okay. At least now is it audible?
Now it's
Is it
audible.
okay, I'll continue then.
Okay, okay. Oh, she can ask. Okay.
Yes, you have to knock me. Otherwise, I don't know. I have no, actually, I have no idea what is happening, what you are listening or not. I have no idea. Okay. Even whether you are able to see or not, that I don't have any idea. Okay, so you have to tell me. otherwise I cannot know. Okay, so this is also very interesting problem. This is from alpha and beta decay. See, there is a nuclear reaction given here, nuclear decay is given here. Oh, so what are the number of alpha and beta particles emitted in the following radioactive decay process? What are the number of alpha and beta particle emitted in the following process? Okay, so the following process I'll write in a bigger font. Look here, this is 90, this is 200, and when it undergoes alpha or beta decay, I don't know how many alpha, how many beta, that I have to find out. So but there is alpha and beta decay, and by that it is becoming a new nuclei that has 168 mass number and proton number is becoming 80. So look, I have to remember one thing. When there is alpha decay, suppose I have a nucleus has mass A. Okay, let me take this as X, A and Z. This is X, nucleus X. It has Z atomic number and mass number A. When there is alpha decay, okay, it becomes suppose some other nucleus. So what happens to this mass number and what happens to this atomic number, that you have to understand. So alpha particle is nothing but a helium nucleus. That means it has mass number A is equal to 4 and atomic number Z is equal to 2. So when this alpha particle is actually leaving the nucleus, then mass number will be getting reduced by 4. Okay, and the Z will be reduced by 2. Okay, this is the thing will happen. Now let me write the same thing for beta decay. So in this case, beta decay in general, beta decay when we say it is beta minus decay, that you have to remember. In general, when we say beta decay means beta minus particle is getting out. Okay, so beta decay means beta minus, and in this case, you know, it has beta decay is actually beta is nothing but in an electron, and in the beta decay we say beta minus. In general, beta decay means beta minus. When we refer beta positive decay, then it is positive decay or positron decay. A positron will be emitting, so that has atomic number +1 and mass number 0. Compared to the mass of proton and neutron, the mass of electron is negligible. That's why the mass is taken to be 0. Mass number is taken to be 0 for beta particle. Okay, look, then when there is a beta decay, what happens to the mass number? Mass number remains the same. Then what changes? There will be change in the atomic number, but how it changes? See, when from the nucleus one negative charge is getting out, then effectively positive charge will be increasing by 1. Effective positive charge will be 1. Now, how many number of alpha particle is emitting? That can be easily understood from the difference of the mass number. Okay, from the difference of the mass number, you look from here. What is the mass number difference here? 200 minus 168. 2 over here. This is 73. Okay, so this is 32. So mass number difference is actually 32. And this mass number difference is happening because of alpha decay only, because beta decay does not change the mass number. So how many, like for each alpha particle, so this is the difference we get in the mass number for the alpha decay. But how many alpha decay had happened? How many alpha particle has gone out or emitted by the nucleus? That can be obtained by just dividing this number by 4, because 4 is the mass number for each alpha particle, as you see from here. So this is 32. So there will be 8 alpha particle. 8 alpha particle. So alpha particle is 8. Now what is, so if there is alpha particle decay 8, then Z actually should change by 16. Z should be changed by reduced by 16. But what is the value over here? Here delta Z, that means change in the atomic number is only 10. Okay, but it should have been, delta Z should have been 16 if only alpha particle is emitting from the nucleus or alpha decay is happening. That means when this change is less than 16, then you have to understand, see, there should be 16 means you should have 90 minus, so this should be, this would have been this. Okay, you should have 74 atomic number over here, but you have greater than that. That means beta decay is happening, because beta decay adds to the atomic number by 1. If there are 6 beta decay, then it will be adding 6 positive effective charge, so that will give rise to 60. That means you had 6 beta decay, okay, 6 beta decay and 8 alpha decay. Okay, so this is how you have to see. So alpha decay, how many alpha particle has been emitted, that can be obtained from the mass number difference, and just by divide. So if you have mass number difference known, divide that with 4, you will get the number of alpha particle. Alpha. How do you get beta? Then you have to see the difference, like what should be the change in the atomic number. If that is not happening, if there is greater than that, then how many positive charge is excess in that many alpha particle, beta particle has been emitted. So this is the thing. So in this case, so we have solved that there will be alpha particle decayed. What is the number? There is number 8, and so this will be the answer. This is the number of alpha particle, and beta particle is 6. So this is the answer. Okay, I hope you have understood. Deepa, you have any question? Do you listen to me or not? Now is there sound? Can you respond?
Clear, sir.
Okay, okay then. So we'll go to the next question then. So this question is also from decay. Here the nuclear reaction is given. I'll write here ZA. This gives rise to YA Z plus 1. So this is what I had actually shown you just in the previous problem. So you have been asked what kind of reaction it is, whether it is beta decay, beta decay, gamma decay, fission and fusion. What kind of decay it is? So since it is the particle, see this is the beta particle, right? So it is beta particle and this is antineutrino. Always beta decay. During beta decay there will be antineutrino. Okay, antineutrino emitted along with the beta particle, and this is massless and chargeless particle. This antineutrino is massless as well as chargeless particle. Anyway, so this is a beta decay. So these reactions you have to actually read, and logically you have to remember some of the reactions. Okay, so this is a beta decay. We'll go to the next question. So this question is also from alpha, beta and gamma decay. So look this reaction, I'll write here in bigger font. X, Z, A. There is some decay, like some particle, whether it is alpha, beta, gamma, I don't know. I'm not writing anything over here, but there is something, some particle decay is happening. Because of that, there is this change happening. So the nucleus, sorry, this is becoming a Y, X becomes a Y, then it has Z, mass number unchanged, whereas atomic number increased by 1, or positive charge, effective positive charge is increased by 1. Then again some particle decay is happening, because of which the nucleus Y transform into a nucleus, new nucleus, that is having mass number A minus 4, and atomic number is getting reduced by, compared to this it is reduced by reduced by 2. Now finally this is remaining the same nucleus, but this star is not here. Now we have to understand what is the meaning of this star. Otherwise these two are the same. B star and B, they have same mass number and atomic number, but the star is missing in the last case. So what is, like, see here the question is, see options you can see alpha, beta, gamma. That means obviously in 3 transformation, okay, or in the 3 steps, either alpha or beta or gamma, whatever it is, whatever may be the sequence, you have to find out. But it is certain that alpha, beta and gamma, these 3 particles are emitted, okay, either of these 3 steps. You have to find out the sequence. You have to find out the sequence, in which sequence the decay is happening, whether alpha beta gamma, or beta gamma alpha, or gamma beta alpha, or first beta decay happens, then alpha decay, then gamma decay. You have to find out the correct sequence. First let us understand this part alone, this part. So in this case you look, when there is mass number unchanged, okay, and there is a atomic number increase, increase in the atomic number, that is by 1. So this happens in case of beta minus decay, okay, beta minus decay or beta decay, I can say. This happens only for beta decay. For beta decay, mass number remains unchanged, but atomic number increases by 1, or effective charge of the nucleus is increased by 1. So this is beta decay. Then in this second case, see, mass number is actually getting reduced by 4. That means what? In case of alpha decay, alpha is a nucleus of helium, so it has 4 mass number. If alpha decay happens, then only the mass number is reduced by 4. That means here it will be alpha decay, and see, there will be 2 like atomic number. If there is Z plus 1, then minus 2. So this will be the new atomic number of the new nucleus, so it becomes minus 1, Z minus 1. Okay, so the second one is alpha decay. So beta decay and alpha decay. Now you have to understand why this star is given here for the nucleus B, and then after some decay the star is missing. What does this signify? This signifies that, see, we have already discussed this. See, in atomic spectrum we have seen there are S, P, D, F, okay, or maybe I can say ground state, then fast excited state, then second excited state. Okay, various states are there, or energy levels are there for atoms to stay. This is what we have already learned for hydrogen atom. Okay, various energy levels we have already discussed for hydrogen atom or hydrogen like atoms on the basis of Bohr's postulates or Bohr's theorem of atoms that we have already discussed. So if it is there for atoms, what about nucleus? Whether they also have various like energy levels? Answer is yes. They also have various energy levels, and you look in case of, you know, the arrangement of the electrons according to above principle, 1s2, 2s2, then 2p6, etc. We have in surprisingly we have these things for nucleus also. Nucleus also we have. That means in nucleus there are various energy levels. Some it is ground state, then it has fast excited states, second excited states, etc. So this star means the nucleus is at excited state. So we know from hydrogen atom, suppose this is the ground state and this is the first excited state, E dot S. Okay, one nucleus is here, sorry, one electron is here. So it always tries to come to the ground state, but it has some extra energy. Whenever it makes a transition, it will emit what? It will emit radiation. Okay, radiation, and that radiation for hydrogen atom or atomic energy, in case of atoms, this energy actually is very less, electron volt order. So it comes under either infrared, then either ultraviolet ray, ultraviolet region, or in the visible region. Okay, these are the region where this radiation fall in. But in case of nuclear energy levels, the difference in the energy levels is actually mega electron volt. When there is a nucleus B in the excited state, it has certain extra energy from its ground state level or ground level. But always nucleus will try to be subtle or come to the minimum energy level where it can be a stable nucleus. So when it makes a transition, it emits radiation of the, like, what is the energy of this radiation? Of the order of MeV, and this MeV order actually falls under gamma radiation region. Gamma radiation. Gamma radiation. So that's why it is called gamma decay. So when it decays some energy in terms of gamma radiation, then it comes to ground state, and this star should be removed. So final state is, or final transition is happening due to gamma decay. Okay. So by gamma decay, a nucleus which has greater energy than its ground state level, it releases the excess energy and comes to its ground state to have a minimum energy configuration. Okay, so this is the sixth question we have. So we have got beta, then alpha, then gamma. Beta, alpha, gamma. So fourth option will be the correct answer for this case. So look, these questions are very, very simple. If you can logically solve in the exam hall, these are very, very simple problem, but these are the problems I have picked up from previous year's question paper of NEET exam. Okay, so go to the next question.
Okay, sir.
Yeah, so I have another, I think I have another 3 questions I'll discuss, then we'll stop the class. You be patient. Okay, you can read the question. Which of the following reasons energy is released in the fission reaction? I have somewhat discussed when I was solving the first problem why energy releases in beta or in fusion or fission reaction. In both cases, what happens? The binding energy increases. What do you mean by binding energy increases? Binding energy increases means they loses some mass. Okay, fission product has lesser mass. Fission product has lesser mass than the reactants. So in this case, look what is the question. Which of the following reasons energy is released in the fission reaction? Let us see. Some mass is converted into energy. So that may be true. Let us read the other options. Total binding energy of the fragments is equal to the binding energy of the parent. This is not true. Total binding energy of the fragments is less than the binding energy of the parent. This is also not true. Total binding energy of the fragment is more than the binding energy of the parent nucleus. This is true. Some mass is getting converted into energy. So this also may be true. So total binding energy of the fragments is more than the binding energy of the parent nucleus. So this is also true and this is also true somewhat, but I don't know whether it is multiple answers are true. Which of the following reasons? Which of the following reasons? That means you should be choosing only one option. Some mass is converted into energy. Some mass is converted into energy, but it is actually not mentioning what mass and all those things. Some mass that may be correct, converted into energy, but there should be some details like which mass, like mass of the products or mass of the parent. So those things are not there. So preferably we actually will be preferring this answer to be the most correct. This is more correct, this is most correct. So we have to choose this one, I hope. So the total binding energy of the fragments is more than the binding energy of the nucleus. Here actually mass is getting converted. Some mass is getting converted into energy. That is true, but some mass of what? Whether the parent or the fragment, that is not mentioned over here. So that's why we may not be choosing this answer, this option to be correct. We must choose this option to be correct. Okay. The total binding energy of the fragments is more than the binding energy of the parent nucleus. Okay. So that should be correct. Okay. So this is again from fission reaction. In any fission process, the ratio of the mass of fission product to the mass of the parent nucleus. I had already answered this question. We are just repeating then. So mass of the fission product. So you have to find out the ratio of the mass of the fission product to the mass of the parent nucleus. It will be always mass of the fission product. Okay, and this is the mass of the parent nucleus. You have to find out the ratio of this. This will be actually always less than 1. This will be always less than 1. So B will be the answer. Okay. Alright, we'll go to the next problem. This is also from fission reaction. So fission reaction means a bigger nucleus breaks into two lighter nucleus. Okay, heavier nucleus breaks apart or breaks into two parts of lighter nucleus. Okay, so here it is stated that when a uranium nucleus is bombarded by neutron has charge 0, mass 1. When it is bombarded by neutron, then what happens to the reaction? This will break into two parts. One part is given, another part you have to identify from here. So what will happen, the first, suppose this is one part, krypton 36, 89, and there will be 3 neutron coming out, 3 neutron, sorry. Neutron, oh, I'm sorry, just 1 minute. I'll write in little smaller font so that I can write in a single line. 92, it is bombarded by neutron 10. So it will give rise to one lighter nucleus, that is krypton. This is 36. Plus 3 neutron. Okay, I'll write the other product. Suppose, okay, so we don't know this, we have to find out, and 3 neutron along with that. 10. Okay. So can you identify, Deepa, which among these will be emitted? You can somewhat check with this. So what is remaining? because neutron anyway they don't have charge. Four, it will give rise to fifth. So there will be element which has mass atomic number 56 that has to be emitted along with krypton. This is krypton, sorry, krypton. So see, 56 is barium, this one. Okay, so barium 56 along with that there will be 3 neutrons. So these are the problems we had solved. So the barium along with barium, so when neutron 23692 is actually undergoing a fission reaction, it will first break up into 2 lighter nucleus. Comparatively, those are krypton and barium along with 3 neutrons. Okay, so we'll stop it here for today. If you have any doubt anywhere, you can ask me, Deepa.
No doubt, sir.
Oh, great. So I'll stop it here. We'll meet on Wednesday, and that day we'll start a new chapter, that is semiconductor. There are, like in semiconductor also, there are many good problems and many good concepts. We'll be discussing all diodes and transistor, etc., and applications of diodes, application of transistors also. So we'll start that chapter on the next day, on Wednesday. So bye for today, Deepa.
Thank you, sir.
Yeah.